Multiscale application is the use of models to explain physical phenomenon that can range in various scales, can be in time, space, or both. There are many complex problems that are multiscale in nature, and the study of fusion plasmas is one of them. There are short-scale turbulence in fusion plasmas that spans in microseconds in time and millimeters in space. And these turbulence would affect large-scale transport that spans seconds in time and meters in space. And as you can tell, this involves a wide range of scales. Fusion, or more specific, is thermonuclear fusion, is the process of fusing lighter, positively charged particles in an extreme temperature, can be hundreds of millions degree, and that would produce heavier particles. And during the fusion process, energy is released. These energies can be quite powerful. In fact, this type of energy is how our sun and other stars power themselves. So we want to bring this power source to Earth because this type of power generation method has many advantages over other types of methods. One major advantage is its fuel availability. So the heavy hydrogen isotopes, deuterium and tritium, that we need for fusion can be easily extracted from seawater and can be produced in the fusion process itself. So the second advantage is that fusion is a clean process. It does not contribute any greenhouse gases, nor does it produce any dangerous, long-lasting radioactive waste like those produced in nuclear fission plants. To achieve fusion in the reactor scales, it comes with difficulties, unfortunately, because we need to heat the plasma to a really high temperature. There are many instabilities arise in that case, and because of that, confining the plasma is extremely difficult. So currently there's an international collaboration called the FET-Future Project, and they're currently constructing a device named tokamak to confine a hot plasma using magnetic fields. This is all as an attempt to demonstrate the feasibility of fusion energy. Therefore, we have an urgent need to understand these multi-scale plasma dynamics that causes confinement disruption before ITER's operation.
Understanding microscale turbulence happening in a fusion device is still an open and very active research topic. And typically, the description of such microscale turbulence needs to be done through a kinetic model. So following turbulence at such a microscale involves a kinetic description. And this is done typically using a gyrokinetic model where the distribution function is described on a 5-dimensional phase space where we follow both positions and velocities. Now, because of the size of the domain and the very small timescales of this time evolution, this is a very challenging problem to be implemented in the code, and it requires usage of advanced HPC techniques. Now, to understand the links between the small-scale turbulence and its impact on confinement and the large scale of the full device, we cannot run a gyrokinetic simulation on long time because for large device such as ITER, it is expected to exceed by far the current computing capabilities of nowadays computers and even the next generation of supercomputers. That's why we will need the usage of multiscale approaches in addition to advanced HPC techniques for modeling these kind of interactions. So first, we believe that designing multiscale applications by coupling together single-scale submodels is a better approach to allow for software of better quality that are easier to maintain and also optimize on an HPC environment. Now, ComPat provide us some tools, open source software like typically Muscle2 or QCG, that allows the developers of the methods and the scientists to really focus more on the development of single-scale submodels and also on the scale bridging techniques. Scientists don't have as much to worry about putting all the ingredients together because this software will help there. So in addition to that, ComPat provides generic way to describe submodels and their interactions, which allow us to monitor the performance, identify hotspots, and provide transformations that can lead to increased performance of these coupled multiscale applications. And that should allow us to run such simulations at full resolutions on large fusion devices such as it.